Okay, acid strength. The strength of an electrolyte depends on the extent of its dissociation. We learned about this in Chem 1A, so this should be reviewed. A strong electrolyte dissociates completely, meaning all of the ions separate from each other. In a weak electrolyte, only part of them, only some of them will dissociate. The strength of an acid is going to depend on its equilibrium. We're going to have equilibrium constants in this chapter. So this is a generic acid, HA. There's no element A on the periodic table. So we use A for acid. It's the acid because it has an A, H plus on it. When it donates this H plus, it becomes A minus. So that's the anion of the acid. This is in equilibrium. So here we have A with the hydrogen, and here we have A without the hydrogen. Here we have water without the extra hydrogen, and here we have water with the extra hydrogen. This is the acid, the base, the conjugate base, and the conjugate acid. I'm sorry, conjugate acid and conjugate base. So a strong acid will ionize completely, meaning it will go completely to the products. There won't be any of this molecule left. It'll all just be the ions. That's a strong acid. It's a strong electrolyte. A weak acid only ionizes a little bit. Well, how do we know which ones are strong and which ones are weak? We have to memorize them. The good news is there's only 6 important strong acids. We only have to memorize 6 acids. If it's not one of those, it's a weak acid. So you need to memorize these. I know it's no fun, but we can do it. So hydrochloric, hydrobromic, hydroiodic acid. So these are the halogens, but the one at the top, HF, is not included. And then we've got nitric, perchloric, and sulfuric acid. Those are the strong acids. We can label acids as being monoprotic, diprotic, or triprotic. Monoprotic literally means one proton. So a monoprotic acid has one ionizable proton, one ionizable hydrogen. So if we look at their formulas, this only has one H. That's all it can give up. This one only has one. This one only has one. A lot of them only have one. Those are monoprotic acids. They'll give up one hydrogen. A diprotic acid contains 2 ionizable hydrogens. So H2SO4, we see there's 2 hydrogens here. So it can donate up to 2 hydrogens. And then a triprotic acid will have 3. Can anybody think of the formula of a triprotic acid? H3PO4. So we learned to recognize this as an acid in Chem 1A because it starts with H. It's got 3 hydrogens. It can lose all 3 of them. Is this a strong acid? No, because it's not on the list. And something we should remember about sulfuric acid is only the first proton is strong. So when you put sulfuric acid into water, this might be coming up on the next slide. No, it's not. When we put this into water, it will completely lose the first proton. It will become hydrogen sulfate ion and hydronium ion. So here it's the acid. Now it has become a conjugate base. But this guy also has a hydrogen ion. Well, I didn't plan this out very well. if you put HSO4 minus in water, it has a hydrogen that it can lose. But it doesn't lose, not all of the ions lose their hydrogen. So this is an equilibrium. This one goes all the way to the right. That's what strong acids do. They ionize completely. This one's going to go to SO4, 2 minus, and H3O plus. But this is in equilibrium. There's still some of this present. Diprotic acid. So strong acids, if we look at an HCl solution, and this is the word, I didn't realize how much my science education had affected the way I talk for a long, long time. I find myself qualifying things all the time because many things have some exceptions, right? And so here, we don't say an HCl contains no intact hydrochloric acid molecules. We say it's virtually none. Because what if there's one? That's not none, right? Scientists got to be precise in how we talk. So virtually none. Practically speaking, no intact HCl molecules. So the HCl reacts completely with water to form hydronium ions and chloride ions. This is a single error, means complete ionization. It's not going to go back the other way. So if we have a 1 molar HCl solution, you put 1 mole per liter of HCl in here, then you're going to get 1 mole of hydronium ions. You're going to get 1 for each HCl. So a 1 molar HCl solution has hydronium ion concentration equal to 1 molar. So this shows it with letters, and this shows it with pictures. Weak acids. So I think of fluorine as being chlorine's little sister, one level up on the periodic table. HF is a weak acid. And so when HF dissolves in water, we get a few hydronium ions, but it's actually mostly HF because it's a weak acid. So when we write this reaction, the HF does react with the water to form hydronium ion and fluoride ion. But we use an equilibrium arrow because this is partial. It's a partial ionization. If we had a 1 molar HF solution, that's not enough information to tell us what the concentration of hydronium is, but we can say that the hydronium ion concentration is less, in fact, much less than 1, because only a few of those molecules will dissociate or ionize. Any questions? So why are some things weak acids and some things strong acids? Well, the strength of the acid depends on the attraction between the conjugate base and the hydrogen ion compared to the attractions of these ions to water. So in a strong acid, we have a weak attraction. In a weak acid, we have a strong attraction. Yeah, that's backwards, isn't it? So I had to make up reasons for things to help me remember. And so well, how can I make sense of this? So the strong acid is very confident in itself. And it's like, I'm an acid, I know that, I don't need to prove it to anybody. I can let that hydrogen ion go. I know who I am. So it has a weak attraction, it's willing to let it go, but it's strong, right? The weak acid, it's like, oh, I don't know, I'm really insecure, I need to hold on to my hydrogen ions or people aren't gonna know who I am. And so it has a very strong attraction to those hydrogen ions, and it only ionizes a little bit. I don't know if that helps or not, but that's what I came up with. Any questions? So, equilibrium constant. Yeah, we're going to be doing equilibrium constants and ice tables in this chapter and the next chapter. So weak acids ionize partially, they form an equilibrium. So here's our generic acid, HA. It would react with water to form hydronium ion and A minus. So we could write an equilibrium constant expression for that. And so that would be H3O plus O times A minus divided by HA. We're not including the H2O because it's a pure liquid and it doesn't change its concentration. So solids and liquids, bless you, are not included. More commonly, we'll write it like this, where we left the water out of it. And so it's like, okay, well, the HA donated its hydrogen. Do we really care who it donated it to? Not really. It donated it to somebody and it became A minus. And so we could also say this is H plus times A minus over HA. So H plus and H3O plus are just the same thing. This is like a nickname, a short formula for it, and this is the full formula. Any questions about that? So sometimes you'll see H3O plus, sometimes you'll see H plus. We mean the same thing. So this equilibrium constant has a subscript A. It's not Kc, it's not Kp, it's Ka. And this is called the acid ionization constant because the equilibrium it describes is the ionization of an acid. So if this Ka is very small, that means we have less ionization, right? Small Ka means it stays over towards the reactants, bless you, and does not go very far to the products. So it's going to be very weak acid, only a few hydrogen ions are going to be let loose. If you have a large Ka, that means more hydrogen ions are released and it's a stronger acid. We don't even talk about an acid ionization constant for strong acids because there's essentially no equilibrium. They just go completely. So here's a table showing a bunch of different acids. Their formulas, their structural formulas, their ionization reactions, and their Kas. Acid ionization constants. So we will be using these numbers. You do not memorize those numbers. There's too many of them. You look them up. The only time you memorize any of these is when you've used it so often that you happen to remember it. Okay? So don't try to memorize those. We'll talk about what pKa is in a minute. Just a quick look at the formulas. Notice that all of these, let's look at this one. All of these formulas start with H. If it starts with H, it's an acid. Those formulas can be written in different ways where it does not start with an H. That doesn't mean it's not an acid anymore. But we're trying to keep things consistent and simple for you. And so we're going to write acids that start with H. We recognize their names because almost always they have acid in the name. This is an exception, phenol. This acts as an acid by donating this hydrogen ion to water. And I would not expect you to remember that phenol is an acid. There's benzoic acid. Is that a weak acid or a strong acid? Weak. It's not one of the six, right? HCl, HBr, HI, HNO3, H2SO4, and HClO4. Consider the three generic acids, HA, represented here, HB, and HC. The images represent the ionization of each acid at room temperature. So we can see that here's a little hydrogen ion, and this is the intact molecule, and there must be, here it is, there must be the anion somewhere. And so over here, we see that there's more hydrogen ions, and over here, so this one has 2, and that one has 4, and this one has 1. Which acid has the largest Ka? It's going to be B. And to answer that, we have to think, well, what does Ka mean? It's the equilibrium constant. I take this acid, and how far does it dissociate? How much of it ionizes? If it's just a little bit, it's going to be a small Ka, and that's a very weak acid, right? So if we're looking for the largest Ka, we're looking for the one that goes most to the products. Any questions about that? Here we've got two acids and their Ka values. Which acid is stronger? Are we looking for the bigger Ka or the smaller? The bigger. Your eyes can play tricks on you, especially when you're stressed out and taking an exam, because this is 8 and that's 4, and 8's bigger than 4. But these are negative, right? So the 6.8 times 10 to the minus 4 is a bigger number than 2.9 times 10 to the minus 8. If you find yourself getting mixed up with that, write them in decimal notation, and then you can see it easily. So here, HF is a stronger acid than HClO, meaning more of it ionizes. It does not ionize completely, but it ionizes more than HClO, which is hypochlorous acid.